in this video I will explain you how you can derive your MOSFET into the saturation region, provided that you keep on increasing the drain voltage. Previously, if you recall, if your gate to substrate voltage is less than the threshold voltage, well, you don't have any inversion layer. There is no channel, so basically your transistor is off. Okay, so that's what we talked in part 3 of this lecture series on MOSFETs. But as you increase the gate to substrate voltage such that it's greater than your minimum required threshold voltage required to establish this the channel, so that you can have a current flow from drain to source. Well, once this channel is established, uh, go, going on increasing the gate source voltage means that you are increasing the electric field from gate to the substrate body. Okay, so the this for the NMOS, you're increasing the channel width. Okay, so this channel or the inversion layer is increasing, therefore you're having more and more charge density. Okay, and this helps the into more flow of current from drain to source. Okay, so for if you are going to increase your gate voltage, okay, which is of course much greater than now the threshold voltage, well, you will have more drain, you have more drain to source current, ID. Okay, so that for a given drain voltage you have more ID. Okay, so the ID is increasing in this direction. Now this is about the transistor, how to turn on the transistor. You need to have a minimum gates to substrate voltage, and that should be greater than the threshold voltage. Now if now if you have this transistor, you have turned on the transistor, so there's you have the inversion layer. Okay, this means you have the inversion layer or establishment of the channel. Then a small applied drain to substrate voltage, drain voltage. It is shown in figure 9a, the thickness of the inversion channel, okay, which exists because of this condition. You have the inversion channel. The layer qualitatively indicates the relative charge density. Okay, so the thickness of this channel of this depletion region will indicate the relative charge density in the region. So which for this case is essentially a constant along the entire channel length. Okay, so this is what we're talking of. This is figure 9a over here. So you have some non-zero application of the drain to substrate voltage. Okay, so you have a gate over here. This is your gate terminal. Then you have the oxide. Okay, oxide is separating your basically this dielectric is between the gate metal and the semiconductor, which is p-type. Okay, so this is an NMOS MOSFET. You see you have an inversion layer or a depletion region over here, and the thickness of this this depletion region, basically this depletion region indicates how much is your how much charge density do you have. Okay, so as you're increasing your VDS over here, okay, ID is increasing, okay, but how far does it go? The question is, if you keep on increasing VDS over here, look at figure 9b, you keep on increasing VDS, the slope of the IV characteristic curve is decreasing. Okay, so you see in part A, this is it basically shows the cross section and the ID versus VDS curve for the N-channel enhancement mode MOSFET. Why enhancement mode? Because you need a gate voltage to create the channel, so this is an enhancement. So in part A you have a small drain to substrate value. In part B you have a larger VDS value. What for VDS less than a certain VDS, call it saturation, VDS saturation. What happens is that, let's try to understand this from this figure. You see, initially, once if you apply a certain VDS over here, all right, this is your VDS basically, drain voltage. Let's call this VDS. You have a reverse biased. You have a reverse biased PN junction over here. Okay, you have a reverse biased PN junction. Um, Basically, this should be like this. Okay. So what happens is that as you go on increasing VDS, as you go on increasing VDS, you are increasing the depletion region across the drain and the substrate junction. So you have a PN junction over here. Okay, this substrate is P-type. The substrate is P-type over here, and you have this n-doped semiconductor region. So basically, you are reverse biasing the PN junction over here, and you go on increasing the PN junction reverse biasing. What happens is that your charge density in the channel, which is already created, because this is increasing. Okay, so this is growing up more and more. So this is going to counter your channel. Okay, so the channel width will be something like this now. Okay, so there will be a gradient. Okay, because of this depletion region due to the reverse biasing of the PN junction at the drain terminal is going to deplete, is going to decrease the width of the channel. Okay, so the channel is going to have a gradient like this. The channel is going to gradient have like this. There will be more charge density around the source terminal and less charge density across the drain terminal. Okay, so what happens is that you are modulating or you are changing the conductance of the semiconductor material. And so if in this region you have less charge carriers, basically you are increasing the resistance of the channel. Call this RC. So this RC increases, the resistance of the channel increases. Well, this turns out to be, the result is you have a lower ID, drain to source current. Okay, and this happens because you increase your drain to substrate voltage. Okay, drain to source voltage or substrate voltage. Both are short circuited here. Okay, this is your source, this is your substrate. So you increase VDS, well you increase the reverse PN junction over here, and then you have a you create a channel something like you have a channel like this. Okay, a, having a gradient like this. It's not an even channel. All right. So having less charge density in this region, you have less charge density in this region. So you increase the basically the channel resistance around the drain region. So this is exactly what is going on over here. So if you're going to increase your VDS over here, you're going to increase this. You are going to introduce a gradient on in the channel, which is something like this. So you have less charge carriers at this point compared to more charge carriers at this point. Okay, this results in reducing ID. So the slope of the ID VDS curve is going down. And if you go on increasing this VDS to a point, let's call this VDS set, what happens is that you have increased the depletion, or you have increased the reverse bias the PN junction so much that depletion width nearly pinches off, or nearly um, produces zero channel width at the drain terminal. So you don't have any channel. So the channel could be like this. Okay, the channel is like this. The width is zero at the drain side. So you can see this over here. Okay, so the width of the channel is zero at the drain side. This is your source. This is your gate. Okay, that's your substrate, p-type substrate, grounded body. So your drain is the channel width is zero over here. There is no charge carriers. So what happens is if you go on increasing VDS, you will have things like this. The channel is going to decrease more and more, more and more. This is shown over here. Okay, so you have this gradient like this. So it doesn't matter beyond this point. Ideal MOSFET will have a constant current like this. Okay, because increasing VDS, like in part A of the figure, you go on increasing VDS, you increase the ID current, drain to source current. Well, that's understandable. Okay, because you have established a channel. But increasing VDS, you should understand that you reverse bias the PN junction. Reverse biasing the PN junction introduces some gradient. Okay, the channel is having a gradient cross sectional width. So you're compromising the charge density at the drain terminal. Okay, So beyond this saturation region, VDS set, basically in ideal MOSFETs, it doesn't matter. You go on increasing since you have reverse bias the junction so much that the ID is no more increasing. Okay, it stays the same. Okay, the first it increases for lower VDS, and this region is linear. So basically, we use this transistor MOSFETs in this linear or triode region. You see in C and D, those C we have reached the saturation region, and in D VDS is greater than VDS sat. So so over here, so you see transistor is fully on irrespective of the drain DVDS voltage. If VDS and this is for a particular VGS, okay. So this is linear region, okay, of the operation where transistor is used as an amplifier. And if let's say the gate source voltage is less than threshold, the transistor is off over here. Okay, so you can use the transistor in saturation and in the cutoff region as a switch. Okay, so these two regions you can use the transistor as a switch. So you can use this as a switch. It is either on or either off. Okay, depending on your gate source voltage. And in this region, this is an amplifier, it's a linear amplifier. So in this region, you can use the transistor for the amplification purposes. So this is the amplifier, linear region. So the corresponding ID versus VDS curves that we've seen in the figure 9b shows that as you increase VDS, the drain voltage increases, all right, and the voltage drop across the oxide near the drain terminal decreases, which means that the induced inversion charge density near the drain also decreases. Yes, the charge density is decreasing because you see you don't have anything over here. There's no channel. There's no charge available in the inversion layer. There is no inversion layer to conduct the current. Okay, so so this is where you drive your transistor MOSFET into saturation. In the incremental conductance of the channel at the drain that increases. Okay, so the conductance of the channel decreases, which causes the slope of ID versus VDS curve to decrease. So you see beyond the VDS set, you see around the VDS set, near VDS set, the slope is decreasing. Okay, you had these two slopes are different. This slope and this slope, there's a difference in these both of the slopes. Because you are reverse biasing the PN junction across the drain terminal, so you are varying the channel width over here. So this effect is shown in the ID versus VDS curves in figure 9. This is figure 9. So you see you have this characteristic curve of the transistor. Okay, so either you can have the transistor in off state if VGS is less than threshold voltage. If you have VGS greater than threshold voltage, then for a certain VDS you have ID. Okay, but if you go on increasing VDS, what happens is that the point comes that the slope starts rising, starts to drop, and then stays constant. Okay, and this is the point where we call this as VDS set. Okay, or the pinch off voltage, because after this you have already compromised the charge carriers at the drain terminal, and increasing VDS beyond this point doesn't help in increasing the current ID. Okay, so this is we call this saturated. The transistor is saturated, is being driven beyond saturation. Okay, and this is cut off. So this is cut off. This is saturation, and this is the linear region, also called triode region or linear region, where you can use this as the MOSFET as an amplifier. Now, so these equations explain the same scenario. You see, as VDS increases to the point where the potential difference between the gate and the drain voltage with respect to the source across the oxide at the drain terminal is VTN. The induced inversion charge density at the drain terminal is 0. So it says the same thing. You're you're reversing the PN junction, and what happens is the other way of looking around it is that you compromise the inversion layer or the channel at the drain terminal. Okay, which means at drain your VGS minus VDS becomes equal to the threshold. Okay, and if you recall, at threshold is the minimum voltage VTN required to establish the channel. Well, if you have reached the threshold, there is no channel. So this is exactly what is going on at the drain terminal. Okay. So if VGS minus VDS set has reached to VTN, well, the induced inversion charge density at the drain terminal is 0. This is what it means. So this effect is shown schematically in 9C. So yes, this is your 9C over here. So this is what is going on. So VGS minus VDS set has reached to VTN. Okay, for this condition, the incremental channel conductance at the drain is 0, which means the slope of the ID versus VDS curve is 0, right? I mean, the slope beyond this point you see is 0. The gradient is 0. So the thing is, increasing VDS, a small increment increase or large increase in VDS beyond the VDS saturation, this beyond this point, does not helps in increasing ID. Okay, ID does not increases. So VDS saturation is the drain to source voltage that produces zero inversion charge density at the drain terminal. So when VDS becomes larger than VDS saturation, the point in the channel at which the inversion charge is just zero moves towards the source terminal. Okay, so the point in the channel at which the inversion charge is just zero, it moves towards the source terminal. You see, the thing is, this inversion layer is moving towards the source. Okay, we are cutting it off. This inversion layer, uh, there is no inversion layer at the drain terminal. Okay, so all of it has moved towards the source. So induced charges are towards the source. So in this case, the electrons which are entering at the channel at the source, they travel through the channel toward the drain, and then at a point where the charge goes to zero, are injected into the space charge region where they're swept by the E field to the drain contact. Since you have the E field due to this gate substrate, so due to the E field, the charges will be swept towards the drain terminal, and you will have the conventional current in this direction, ID. Okay, so you will have a conventional current ID in this direction. This is due to the field that is being established by VGS. So in the ideal MOSFET, the drain current is constant for VDS beyond VDS saturation. This region for ID versus VDS characteristic is known as the saturation region, and it's shown in 9D. So this is the saturation region we are talking of. Okay, because ID is not increasing with respect to VDS. Right. So as applied gate to source voltage changes, the ID versus VDS curve changes. So you can have a family of curves. Okay, because from the equations, since VGS is changing, it shows VDS. It shows the basically the saturation saturation points are changing. So it shows that the VDS saturation is a function of VGS. Therefore, we can generate a family of curves for the N-channel MOSFET. So what happens is that when you increase your VGS, increasing VGS will create more charge carriers. Okay, so this your channel width is increasing like this. So the channel width is increasing like this. You have more and more, and since you're increasing the electric field from VGS, which is much beyond than the threshold required, there is a minimum required to establish the channel. You have more and more induced charges. Okay, you have more and more negative charges, which is attracted to the bottom of the oxide layer. Okay, so what happens is you have more current. As a result, you have more current due to more charge density. So you see increasing VGS. This is VGS1, VGS2, VGS3. You increase VGS, you increase ID. Okay, basically your ID is increasing in this direction due to VGS. This VGS5 is greater than VGS4. VGS4 is greater than VGS3. So increasing VGS is basically you are increasing the channel width, and owing to more channel width, you have more charge density, and due to more charge density, there is more flow of current, right? So this is being shown by this equation. So you have more family of curves, which is shown. This is your figure 10. This is your figure 10. So the region, now you have those points for each VGS. You have a cutoff, or call it saturation, VDS saturation. This is VDS saturations, and from this family of curves, you can see that you have the non-saturation region where VDS is less than VDS saturation for the given VGS. So this is where you are going to operate your transistor as an amplifier. Okay, this is where it's operated as an amplifier. On the other two regions where VGS is very small, let's say VGS is 0, you drive your transistor in cutoff. So this is a very small ID current, possibly a leakage current. So this is where the transistor is off for the red curve. Okay, this is where the transistor is off. And then as you go on increasing VGS, you drive it in saturation, go on increasing VDS as well. So that's your saturation region, and over here and in this region, the transistor can be operated as a switch in this region and this region. So the region for which VDS is less than VDS saturation is this region. Is this region, okay, for which VDS is less than VDS sat. This is called the non-saturation region or the triode region. So the ideal current voltage characteristics in this region are described by the equation. You can see this Kn parameter is a transconductance parameter having the dimensions of ohm inverse or Siemens, okay, because it's relating the ID current with respect to the voltages, right? So we'll talk more about this conduction parameter. This depends on the fabrication or geometrical parameters and electrical parameters of the MOSFET. Okay, so in this region and in the non-saturation region, you can relate ID with VDS from the following expression, from the given expression. Okay, so the family of ID versus VDS curves for the n-channel enhancement mode MOSFET. Note that VDS saturation voltage is a single point on each of the curves. So you see these points, they are single points for each given gate to source voltage. Okay, and if you join these points, the region on the left, towards the left, is where you are going to operate the transistor as an amplifier in the triode region or non-sat region. So the point denotes the transition between the non-saturation and the saturation regions. Because beyond this saturation region, ID is not going to increase, so the MOSFET is saturated. Okay, and that is the condition VDS greater than VDS sat. In the saturation region, the ideal current voltage characteristics for VGS greater than VDN are described by the equation. So we are talking of saturation region right now. The ideal characteristics are given by the following equation, where Kn once again is your transconductance parameter having a dimension of Siemens. In saturation region, since the ideal drain current is independent of drain to source voltage VDS, so you see increasing VDS does not affect ID at all. So the incremental or small signal resistance is infinite. Okay, so what it means is that even if you increase, there is a small incremental increase between the 2 points. Let's say since the slope is 0, you have a small increase in VDS over here. Let's call this as delta VDS. Okay, which is finite, which is of course which is greater than 0. The difference is greater than 0 between 2 points. Divided by if you divide this expression with okay, divide this by ID, delta ID. There's no change in ID. Basically, delta ID is 0 for a constant VGS, for a certain VGS, and that is 0. Okay, so there is no change in ID. So if you are going to divide this by delta ID, well, this means that the slope is 0. Slope of IV characteristic curve is 0 in the saturation region, or you can say the small signal resistance is infinite. Is infinite. So R naught, let's say R naught, small signal resistance in the saturation region for a small change in VDS corresponds to an infinite resistance, because there is no a change in ID. Okay, no change in drain to source current. So in the saturation region, the ideal drain current is independent of the drain to source voltage. The incremental or small signal resistance is infinite. Okay, this is infinite. R not infinite. The parameter Kn, which we talked earlier, is called the transconductance parameters for the n-channel NMOS device. So for simplicity, we will refer this parameter as a conduction parameter. Okay, this can be described in terms of the, so W is the width of the channel, so width of the gate. L is the length of the gate. I think we have seen this previously. You have seen this L and W. Okay, this is the length over here of the gate, and where is the width? Okay, this is the width of the gate. This is L, this is width. These are two geometrical parameters, okay, which are set in the design constant. Designing of these are geometrical parameters set during the fabrication process of MOSFETs. So K is dependent on these geometrical parameters and the electrical parameters. Electrical parameter Qx is the oxide capacitance. Okay, this oxide capacitance exists between the gate and a semiconductor. So you have a finite oxide capacitance, which is per unit area. Mu n refers to the mobility of the charge carriers in the channel. Okay, this is the mobility. So these two parameters, mu and Cux, are these two parameters are the electrical parameters of MOSFET, whereas W and L are geometrical parameters of the MOSFET. So the capacitance per unit area is given by epsilon is the permittivity of the oxide, Tux is the thickness of oxide. Okay, so if you recall, we have defined this thickness Tux over here. That's thickness of the oxide. Okay, and this oxide has a permittivity of epsilon Ox. Okay, so this is the permittivity of the oxide. Could be silicon dioxide. Okay, and dielectric. Between the gate having a width W and length is capital L. So that's how you express your parameter transconductance parameter in terms of those parameters. So for silicon, for example, the relative permittivity is 3.9, and that's how you find the permittivity in farads per centimeter. The parameter mu n, previously seen in the expression of Kn over here, over here, this mu n parameter is the mobility of electrons in the inversion layer. Okay, so the channel width and the length are the MOSFET's gate geometrical parameters. These are the gate geometrical parameters. The conduction parameter Kn is a function of both electrical and geometrical parameters. The oxide capacitance and the carrier mobility are essentially constant for a given fabrication technology. However, the geometry or the width to the length ratio is a variable. It's a variable in the design of MOSFET and used to produce specific current voltage characteristics. Isn't that right? Because where is this Kn? Kn is present in the non-sat region, and you see this the same parameter present in the saturation region. Okay, so this Kn, which is proportional to the ratio of width to the length of the MOSFET, is basically you are controlling the current from this parameter. The drain source current is dependent on the geometrical parameter of the MOSFET, okay, which is that's how it is fabricated. With these parameters, the transistor is fabricated. So if you are going to select your width to length ratio as such, well, you can select you're selecting or you're defining your IV characteristics from this parameter, the transconductance parameter, capital Kn. Okay, so we can write the conduction parameter in the form small kn prime over 2 W over L. Again is the geometrical parameter of the MOSFETs. The W and L is the dimension of the gate. So Kn again over here is the product of mobility and the per unit capacitance of the oxide. It's called the process conduction parameter. Normally Kn is considered to be constant for a given fabrication technology. Once you have fabricated the transistor, the W and L are finite and they are fixed. Okay, so but this Kn has a role to play in defining the current and voltage characteristics. Okay, so you see that in both non-saturation and saturation region, the current ID over here is dependent on this parameter Kn. Okay, in both regions over here as well, in saturation region as well. So the width to the length ratio is transistor design variable.